So let's start today. So you all remember this data, don't you?
Yes, Doc.
I'm sure by now you know that I do ask a lot of questions. So some of you should get your hand on your microphone to unmute yourself to be ready to answer the questions. Because I will be talking a lot by asking you a lot of questions. Now, the W1 and the W2 are representing the inputs X1 and X2 prices. That's what they are representing. Do you guys hear some noises? All right, so this is the data set. Now you can see that the data set is in time period 1 and time period 2. Do you see that?
Yes, Doc.
Yes, please.
It's in time period 1 and time period 2. So what we're going to do now is to plot the data set. You know this plot already. This is just a recapitulation. You plot the data set, indicate the input and output, create the frontier, and then generate your radial lines. So this is all that you have here. There's something I want you to note. We learned it the last time. I want you to understand it here again. Technical efficiency is measured as the distance to the frontier divided by distance to the. I want to repeat that. Technical efficiency is distance to the frontier divided by distance to the firm. But distance function, which is what you see on this up here, the distance function is defined as distance to the firm divided by distance to the frontier, because it's a reciprocal of the technical efficiency. So please keep this in mind. Memorize it if you have to. Technical efficiency is distance to the frontier divided by distance to the firm. And the distance function is distance to the firm divided by distance to the frontier. Is that clear?
Yes,
Yes,
sir.
Doc.
So keep that in mind. That is what gave us the efficiency score for E. Okay, the efficiency score for E to be 66.7%. All right. We've done this previously. The frontier is the boundary of the frontier. Yes, Emmanuel, you have a question.
Yes, please. So with the formula you gave for the technical efficiency, distance to the frontier over distance to the DMU, I want to know whether it applies for both the input and output orientation.
Yes, that applies to all orientation.
Okay, all right, thank you, sir.
It's the same, it applies to input and output orientation. It doesn't change. Yeah. Okay. It is a reciprocal factor. It applies to both input and output orientation, but the interpretation will be different. The interpretation of the, of the value will be different, especially given the reciprocal factor that we've always been mentioning. When we come to doing output-oriented one, you will understand what I mean by the interpretation is different. All right. So this is a that we have here. Now we are going to bring cost boundary. Okay, so I want you to look at this data. And I want us to add the cost to it. Now I'm going to show you how you can bring the cost to this picture and how the cost can be used to help. In fact, not the cost alone, but it's called the ISO cost. Now, do you know that the blue line is the ISO cost? That blue line is the isoquant. Now, what is the difference between the normal standard microeconomics isoquant and what you have here? Who can tell me the difference between the normal isoquant that we know and what you are having right here? There's a slight difference. There's a slight difference between the normal isoquant and what you have here? Who has an idea? Yes, Edwin.
And say the normal isoquants are smooth lines or
Exactly.
smooth curves.
Exactly. So that one looks more at absolute efficiency. And this one looks at relative efficiency. Take note. So that one, there is no piecewise line. As he said, it's a smooth curve, which is really not that easy to obtain. So that is it. But we will still call this blue line an isoquant. And every isoquant, to get costs, you need an isocost. Now, to be able to get the isocost, you need to be able to go to the prices of the inputs, isn't it? So I'm going to go to the prices of the input here. These are the inputs. So the inputs for DMU A, input X1, which is 3, input X2, which is 5. Their prices are 3 and 3. You can see that we've given one price for all of them, the law of one price. So we are assuming that they are all charging the same price. Of course, that is an assumption that has to be relaxed in real market systems. But according to Fair et al., Farell, and all of that, this was an assumption that will be useful. But we are going to use that principle. And you remember that in the world of tone, we indicated that this assumption is flawed. Do you remember that the whole principle of perfectly competitive market was changed in the tone's cost efficiency? You remember?
Yes, please.
All right.
Yes, please.
So now we are going to create the isocost line. It's like the budget line of an indifference curve. In fact, this whole thing can also represent, the blue line can represent an indifference curve in a consumer theory. And the budget line can represent the isocost in the consumer. All of these are possible because of duality. So how did I get this isocost line? Now, first of all, please look on the top here, cost efficiency. What is the definition of cost efficiency? It is the minimum cost, which is a numerator, divided by the actual cost. It is a minimum cost divided by the actual cost. So first of all, we need to know the actual cost for every DMU. Now, how do you get the actual cost of every DMU? Well, look at the calculation. It is a summation of the price of the input multiplied by the input. Do you all see what I see?
Yes, sir.
Yes.
So it's W multiplying the X. So let's come here. This is it. So the total cost for a particular DMU is the W. So for DMU1, I made a mistake here. For DMU1, it will be W1 multiplied by that. Let me just slightly alter it. So the first thing you want to do, just a second. So
Yes.
let's do for DMEB. Just take you back to DMEB. This is DMEB. Want to calculate the total cost for DMEB. And when I finish with that, I'll let you guys calculate the total cost for every other DMU. This is how it goes. For the total cost C for DMUB, it is going to be the W1 for DMUB times its input 1. And then the price of 1 input 2 times the input 2 itself. Now, if you go to the data set here, if you look at B, the prices are 3 and 3. So for all of them, the prices are 3 and 3. Now, when you look at the input for B, input 1 is 3, input 2 is 3. So that is how come we get something like the 3, which is the prices, and then the 3, which is for the input. So 3 times 3 will give you 9, 3 by 3, 9, 9 plus 9 will give you. Do you understand how I was able to calculate this?
Yes, sir.
what I want you to do now is I want you to calculate the input, the actual input for DMA. I want you to do for DMA and tell me the answer you had. Tell me your answers. This is the data. I'm going to ask you to tell me your answers. So first thing, I want the actual cost you had for A. Actual cost you had for A. Edwin, what is your value?
24.
24. Joyce, what is your actual cost for C? Joyce, what is your actual cost you had for C? And type into the chat because your voice. Type into the chat. Your voice is not good. Derek, what is your actual cost for D?
30.
30. Deborah,
Yes, sir.
actual cost for E?
31.5.
Okay, 31.5. So these things that I'm letting you calculate so that you know exactly what is happening. But one of the things I've seen people do is that they see the thing, but they don't know what is really happening until you do it. So that when you create your own fictitious data set, you know exactly how you are going to go about it. So those are the actual costs that you can get. I'm going to take one of them and then draw the ISO cost for that. So I'm going to take that of B, DMUB, and then draw the ISO cost. Now, when you draw the ISO cost, you take this same formula, C equals to W1x1, W2x2, and then put the value of the actual cost there, which is 18. Then you substitute the prices, but you'll be left with the inputs. So you have the prices, which is 3 and 3, left to the input x1 and x2. Because the Cartesian plane that you are having here, it's a Cartesian plane for x1 and x2. The idea is that you are going to draw this equation of a line. If you look at this carefully, okay, in this blue 18, 3x1 plus 3x2, this is the equation of a line. So equation of a line will mean that you assume that x1 is 0, what is x2? You assume that x2 is 0, what is x1? So looking at this, what would be the value of x1 when x2 is 0?
6.
What is the value of x2 when x1 is 0?
6.
Okay, so now we know that the coordinates of this is going to be 6 and 6. Okay, so we know that. So we now have a value of 6 for x1, 6 for x2. So what you are going to do is that you're going to look on the graph, okay, and then wherever you see 6, you note it down. Wherever you see 6 here, you note it down. And then you join the 6 to the 6. You create a kind of a zigzag line. Okay, and then that zigzag line, you can shift it up or down until the last place it becomes tangent to the isoquant. Now, in our case, it's just coincidental that it becomes tangent to the isoquant right here, at the same point of B. And so what it means is that that point B is the coordinates there, which is 3 and 3, are going to be used as the minimum cost point for DMUB. Now, because it just happened to be at the B, it will not make a full sense better. So let's get a different one. Okay. So what I want you to do is to get another one. Let's take DMUA. Okay. If you do DMUA, what will be the equation of a line for the DMUA? You said you got the value of the total cost to be what?
24.
24. Okay. So now let's go to the variables. For DMUA, we have 3 and 5. 3 and 5. So let's write something. Let's write something like 24 equals to 3 for the x1 and then 5 for the x2. And then what what you are going to do now is to find the value of x1 when x2 is 0, and the value of x2 when x1 is 0. So the value of x1 when x2 is 0 is what? This is a quick 24 by 3
8, sir.
is 8. And the value of x2 when x1 is 0 is what?
4.8.
4.8. So you now have 4.8, which is a x2. Okay. And then, let me just clean this. You now have 4.8, which is a x2. And then you have 8. So what you are going to do is that 8 is the x1, 4.8 is the x2. So you now go to the axis here.
And hello, Doc. And Doc, please, why are we using 5?
Sorry?
And please, I want to know why we are using 5.
We got the 5 from the values of A. Look at the value. You have 3 for the x1 value. Oh, sorry. We have to use the
W1 and W2.
we have to use the value 3 and 3.
Right, sir.
It's 3 and 3, right?
Yes, please.
No.
Yes, it's 3 and 3. He's right. So we change this value. Change the 5 to 3. So it's going to be 8 and 8, isn't it?
Yes, sir.
The value here is going to be 8 and 8. So you now go to the graph. Everything. So it's going to be 8 and 8. You now go to the graph. And then you now plot 8 and 8. And actually, when you plot 8 and 8, it's not showing here. It will go above here a little bit. And so the graph will be like a very, zigzag graph at the top, passing through A. And so if you want to know the last place where it touches the tangency of the isocant, when you shift down, because the graph is going to be like something like this. Let me just draw it slightly here for you. Because it's going to be 8, the graph is going to be something like that. And as you shift it down and shift it down and shift it down and shift it down, it's still going to be at the tangency point of B. Do you get it?
Yes, sir.
So that is how you get an isocos line for that particular DMA. This is according to Farell et al. Now, let's do another one for E. Let's do another one for E. Let me clear everything. And let's do another one for E. Okay. So let's go DMUE. What value did we have? We had 31.5. Okay. So once again, you are going to pick 31.5. Once again, you're going to pick 31.5 equals to 3x1 plus 3x2. And that will give you a certain value. So find it for me. 31.5 divided by 3.
10.5.
You're going to get 10.5, 10.5. Okay. Also above. And so when you shift it down, where will it be? Okay. Our graph is quite big, so I will not be able to showcase that. Because to actually showcase 10.5, 10.5, that would mean that we need to go way above this value of 6. And then the idea is to shift it down to the last point where it exceeds. So the key point is this. The last point where the isocost is tangent to the isoquant in a parallel fashion, that would be the minimum cost for that.
Amen.
That would be the minimum cost for that particular DMU. And so this is how you are able to determine the minimum cost, okay? And then for each one of them. So we are able to now get a minimum cost. How do we now? So in this case, we've gotten the tangency. How do we now estimate? And listen carefully here. How do we now estimate the cost efficiency? Well, the cost efficiency is calculated as the distance from the isocost to the DMU. So let's say I want to calculate this particular DMU, B, okay, and I want to calculate its cost efficiency. It is the distance from the isocost to the DMU. Without even calculating, you will know that the cost efficiency for DMU B is going to be what value?
Doc, it's going to be 1.
It's going to be 1. Okay. Now remember that when we found the isocost line for A, it was actually up here above, and we moved it parallel fashion downward, and at the last point at the left, the isoquant was also at the point B. So we can still use this zigzag black line to also represent the isocost, the minimum isocost for A. And so the cost efficiency for A will be the distance between J and A. Between that distance, how do you get it? It is OJ divided by OA. OJ divided by OA. So that is how you calculate it. So OJ, if you look at the graph down here, OJ will give you a value of what? When you read it on the X1 axis.
2.25.
2.25. So OJ will give you a value of 2.25, and OA will give you a value of what?
3.
And so the cost efficiency for DMU A will be 2.25 divided by 3. That is the cost efficiency. And on the basis of that, you guys should be able to calculate the cost efficiency for every single one of them. So I want you to do that. Calculate for A, B, C, D, E. Calculate the cost efficiency for every single one of them. This is by graphical calculation.
Doc, please, I have a question.
Right.
So are we looking at the cost values at those points, or we are just taking the quantities at those points? So 2.25 over 3. Or
Yes.
we are looking at the cost values.
But we are not looking at the cost values here because we are not.
Distance on the frontier.
Who's talking? Someone is talking and I'm confused.
Oh, sorry. I was talking to myself. I was trying to understand.
So you just mute yourself and then let's move on then. So you calculate, Dana, we have not impounded the cost. We have not impounded the
Okay.
here.
Okay.
We are just using the fair etal approach.
Okay, Doc.
All right. So it's going to be 2.25 over 3 for the A, and it's going to be 3 over 3 for the B. What will be the C?
4.28 over 5.
What about D? You see, I deliberately left out D so that I did not draw the radial line for D so that you can use your own imaginary eye to be able to get it. But what about E? What would be the cost efficiency for E?
Doc, please, E would be 4.28 over 7.5.
All right, you are thinking. You are really thinking. So that is how you calculate it. You should be able to calculate all of them. Of course, if you are doing a graphical interpretation, it's only for illustrative purposes, so you don't have to do it. Sometimes you can use the software to get you the answer, but you must know what the software is doing. That's why I'm using graphical interpretation. And all of this are along the radial line. Don't forget, they are radial line measurement. Now, how do you calculate the allocative efficiency? The allocative efficiency is the distance between the isoquant and the isocost along the radial line. Along the radial line. So if you are calculating the cost efficiency for A to be G OG over OA, then the allocative efficiency there is the distance between the isocost and the isoquant along that radial line. So in the case of A, it will be what? In the case of A, what is it going to be? It's going to be the same thing, isn't it?
Yes, Doc.
It's going to be the same thing because the distance between the isocost and the isoquant, okay, for A is the same as the cost efficiency value. For B, it will also be the same thing. What about for C? For C, what will be the allocated? What will be the allocative efficiency for C?
Doc, this is the same thing.
What same thing? Mention that same thing.
It would be the same value as the cost efficiency, which would be 4.28 over 5.
Good. What about E? Now we didn't do E for cost efficiency. Oh, we did E for cost efficiency. So what would be the allocative efficiency for E?
Doc, please, for E, it would have the same allocative efficiency as C, which would be 4.28
exactly
over 5.
So you can see that E will have the same allocative efficiency score as C, but they will have different cost efficiencies. So graphically, that is how you estimate allocative efficiency and cost efficiency. And when it comes to how you estimate technical efficiency, I'm sure you all know it. The distance to the frontier divided by the distance to the frontier. Remember, I'm using efficiencies, technical efficiencies. I'm not using distance function. So everything that we are calculating, the reciprocal will be the distance function. So take notes. All right. Any question on this? So on the basis of that, we can calculate the cost efficiency. In fact, mathematically, this cost efficiency calculation is what I've done here. But another way of calculating it is the minimum cost over the actual cost. This is what you see here. So the minimum cost for B, okay, that is where it's last left the tangency was 18. You all remember that. The maximum, the actual cost was also that same value. So you have the minimum cost over the actual cost. All right, okay, so let's continue. So this is how you calculate for every single DMU. So for A, you can see that the minimum cost was 18. It's the same minimum cost you are using for all of them, divided by the actual cost. And you will see that that will match up the graphical computation that you did. That will match up that graphical computation that you did. Of course, the allocative efficiency, you have been able to detect it all on. So this is allocative efficiency for E. So on the basis of this, I can summarize my results. Okay. That the minimum cost, which is what you see on the numerator, divided by the actual cost, which is what you see on the denominator, that is what you see. So on this graph here, and this is what you want to do in your normal thesis. Okay, you have your data nicely like that. You have your minimum, your actual cost for each one of them. You have your minimum cost for each one of them. You have your cost efficiency. You have your technical efficiency, and then you have your allocative efficiency, which is the cost divided by the technical. That's what you want to do. That's how you want to calculate this. Use this principle, because this principle is what we are going to build on when we come to productivity. That's a principle. No question. All right.
Hello, Doc. So please, this means that with the minimum cost, all the DMUs used the input levels of DMUB. Is that it?
Well, in this context, yes.
Yes.
This context, because it will happen that there will be some other data set you will have where them are using the input, the tangency point will be for DMUB, another firm, this tangency point will be for DMUH, another firm, its tangency point will be for DMU3 and D. So it can be different along the lines of Fair and Farell.
Okay.
Along the lines of Fair and Farell. However, when you are doing for tone, they will all be using the same minimum cost, like this one. When you are doing for tone, they will all be using the same minimum cost. But with this one, this very one, the reason why they are all kind of using the same minimum cost is because the data sets, in fact, even in technical efficiency, only one of them was technically inefficient, isn't it?
Yes.
So the firms are not many enough. So this is very brief, quick. Okay. Now, Diana, you will notice that I did not fully get into the intricacies of the tone. But actually, if you go into the tone, it will be the same thing for this data set.
Okay.
So what I plan to do is to use it, and if I go to the tone, because it's going to be the same for this data set, you guys will not really understand it because it's going to be the same. So I'll use a different data set, which I already have.
Okay.
Of course. And then I'll use that to walk you through the difference between the tone one and the fair eta one.
Okay, Doc.
I'll do a different video on that.
Okay.
Now, any question? We are ready for mom quiz.